Thank you very much, Nick. Good evening and welcome to everybody. I'm very happy that we can host here at City this event, this AES Cutting Edge event. I would like to give you an overview of the research we do in the Music Informatics Research Group here at City. Before Zoran will give you an overview of the research at the audio labs at King's College, and Diana will tell you about what's going on at the music department in terms of music technology. So the Music Informatics Research Group is active since about 2005. And we are in the Department of Computer Science and that's now the School of Mathematics, Computer Science and Engineering, recently renamed. And we are at the moment quite a few people. So it's myself and Emmanuel Banitos, Den Tidar, and Daniel, who are working as researchers in the DML project. Also Alexander Kachkev, who also joined very recently. And we have 3 PhD students who are also, 2 of them are also here, Vinir, Srikant, and Andreas. No, sorry, 1 of them is here. And we work mostly on connecting music audio and music structure. That's the main interest that we follow. And for that, we apply that in music information retrieval, music signal analysis, computational musicology, and most recently, big data for music analysis. We have a few projects going on. The Digital Music Lab is a project that we work on with the British Library, Queen Mary University here in London, and UCL. And audio symbolic similarity models with Lancaster University, UCL, and also British Library, and semantic linking of radio data with Oxford, BBC, and Goldsmith. Yes, and I want to give you a few examples of the things that we do. So audio music transcription, that's mainly Emmanuel's work, and we work on multi-pitch detection, including multi-instrument identification and joint pitched and unpitched detection of notes. And this is generally a hard problem in signal processing and computing. And I'll give you a little example. Here's an old recording from the Charm data set. Oops, sorry. Let's try again. Okay, and when we want to analyze this kind of audio signal, we are interested in the notes, and extracting the notes is, as I said, well, it's a relatively hard problem, but it can work quite okay. So here's the result we get. Okay, you can hear it's not perfect yet, but this is about state of the art, and this is something that helps us to look deeper into the musical structure of audio recordings, because we know where the notes are, at least with, well, not 100% correct, but with a good degree of accuracy. One of the focus areas of this group is music language models, what I call music language models. It's modeling patterns and structures in music. So like a statistical language model in natural language research. And we do things like melody prediction. So that enables us, for instance, to model musical styles in terms of their probabilities of notes following each other. And that can be used for classification or for musical voice separation. So that's not from audio in this case, but it could also be applied to audio. So that's one of the future plans. Polyphonic prediction is a very hard problem, so you don't get good results in that as such, but it can still be useful for applying it to automatic transcription and improving the performance of automatic transcription. Voice separation is something we do meter and rhythm modeling, and we use the typical techniques we use for this are neural networks, probabilistic models, and more recently networks of oscillators that give us the opportunity to encode some or to detect some of the temporal structures, temporal repetitions, the metrical and rhythmical structure of the music. So these music language models are then useful to help with other tasks like voice separation. So one PhD thesis that is currently being close to finishing is on the voice separation on lute tablatures. So a lute tablature looks like this, but without the colored lines. And it gives you no indication of the polyphonic structure, which note belongs to which voice. So that is the problem we're trying to solve by giving a good estimate of which note belongs to which voice. So basically inserting the colored lines and then enabling transcription into modern notation. Another example I just mentioned is that if you have a probabilistic model or a neural network model of the musical style you're working with, then that can be helpful in the transcription because it gives you a better estimate which notes are likely to come up next in the audio. Okay. Another area we're working on is music similarity modeling directly from audio, and that is it's basically a complex and concept because we don't really know very much about what makes people perceive music as similar. We don't have a very clear picture on that. We have some idea, but so we're using machine learning to learn more about it in trying to also take into account some elements of context in the form of metadata, but there is also, of course, culture and psychoacoustics. And the computational similarity models that we work with then assign different weights to different features. And so interesting question is which features are important and how can we find that out, or how does it play out when we apply our algorithms. So here in this example, this is a matrix of our feature set, and the weights, how they change when we specialize a model from a more generic one to one that is specific to the German data set or German data subset that we have. And we can see that there are some, at least in our data, which may not be very representative, we can see that that there are some aspects of the music that play a larger role than in general in the other parts of the data, and there are some aspects that play that are less important. So this doesn't necessarily tell us very much about the music yet, because the data set is small and there are some aspects of the features that are not well, there may be more features that may be relevant that we're not capturing here, but it is a very interesting approach, and it helps us to get a better model of music similarity in practice for things like music recommendation. We do collect data for this with a little game that is you can play on Facebook or on the internet, and that you can also play here. So we have a computer where you can later on try it yourself. So the idea is we collect similarity data by presenting 3 pieces of music, and you choose the one that doesn't belong to the to this group, so the odd one out, which tells us that this one is less similar to each of the others than the other two among themselves. Okay, I skipped the video I have of this. You can play it yourself to keep within the time. The final aspect I want to show is our most recent project, which is called the Digital Music Lab, where we work on big data technology for music analysis. So one of the most recent developments is that we get more and more data, and the technology is being developed to process this, to make predictions, to recognize trends and patterns, and we want to apply this to music audio. So the idea is that we join music information retrieval technology or methods with big data technology, and also the concepts that of musicology, so that we want to recognize more of the structure of the music on a large scale, so that we can detect trends, for instance, over time. For this, we're developing an infrastructure, software infrastructure, with tools, using existing tools, putting them into this larger context, and creating visualizations. And the idea is that we want to share this infrastructure so that others can do the same, and we accumulate and share more analysis data, which enables us to get a better picture of music. And at the moment, we are working with the British Library and with a company called I Like Music. And so we have a data set of over 1 million tracks. And we do things like visualizations of chord patterns. And this is something that hasn't been done before on this scale. So we kind of need to find out how best to display the data and how to make use of these new technologies. Another interesting result more recently is that we looked at temperament. So extending an earlier study, looking at different temperaments in harpsichord recordings and how the use of temperaments develops over time. So you can see here the different lines that in different decades you find different frequency of recordings of these or of the temperaments in the recordings. Yes, that's my overview. So these are the things we're working on, and we have posters here where you can talk to our researchers and find more specific information, and also try some of our software. And yeah, if you have any questions, then feel free to ask.
Okay, well, in this case, maybe we should welcome, thanks, Tilman, and
Okay, I'm going to just give a brief introduction to our research, which is described technically on these posters here in demo, and that is a new technology for perceptual sound field reconstruction, recording, and synthesis. And this is joint work with Enzo De Sena, who is here now, who was my PhD student, and now he's with Catholic University of Leuven as Maria Curie Fellow, and Hussein Habiboglu, who is now assistant or perhaps already associate professor at the Middle Eastern Technical University in Ankara. So before I go give some details, I would like to acknowledge James Johnston for introducing me into this research back when we were both at AT&T Shannon Laboratory, then Francis Ramsey for providing his support, critical support in the early phase of this research, and then of course EPSRC for funding it, and also for additional funding from the Faculty of Natural and Mathematical Sciences at King's College. So what are aims and objectives of our technology? It's like basically whatever is the holy grail of surround sound systems, that is actually to be able to record technology which would be able to record musical performance in original venue and then reproduce it in such a way that the listener feels transposed or feels that he is really present there where the music recording was made. And also to provide a convincing illusion of an event in a desired virtual space, actually for all kinds of virtual reality applications, including video games, etc. So that is nothing really new. And to that end, what we want to do is first to understand principles involved, scientific principles. Based on those principles, provides a general, scalable, and reconfigurable framework, which would be applicable to any number of channels and possible different kinds of layouts of speakers, and also provide practical solutions. So state of the art. So the experience of spatial sound can be provided in many different ways. In one hand, in one side of the spectrum, we have wave field synthesis techniques, which are actually aiming to provide a physical approximation of the sound field. And therefore, wave field synthesis is actually able of providing large listening spot to a very, very large group of audience listeners. However, it requires a very, very high number of channels, and computation complexity and equipment complexity is very high. At the other side of the spectrum are binaural techniques, which rely critically on psychoacoustics, where that is they create those so-called ear signals, which are then reproduced over headphones or over two channels, in order to provide sweet listening spot for just listener for the audience of one, or maybe very, very small group of listeners. So in between are the slow channel count systems, 5 to 10 channels, which are actually aiming to provide some sort of stable listening spot in a limited area for like a small group of listeners, and that unfortunately happens to be the largest, the segment of the techniques which actually is most prevalent in commercial systems, but on the other hand, it's actually least understood of all techniques. We know how to do wave field synthesis. There isn't really much mystery about that. So we just have all these mathematical equations, and if we cannot solve it, there would be always mathematicians who would be able to do it. And pretty much lots of it has been understood about binaural techniques. That is what kind of binaural auditory cues that we need to provide into 2 years to actually have a desired experience of sound source localization in the plane. So these low channel count systems that we are concerned with are yet to achieve spatial realism that is possible with available channels. And the reason behind that is mainly due to the legacy of sound production for film industry, because that was actually what was driving progress for many years. And however, the main goal of the systems was actually just to create some sort of attention-grabbing sound effects and some sort of general ambience feel, without actually trying to sort of make them consistent, mutually consistent and consistent with the acoustic or physics of a natural space. So they're actually then heavily mixed, and sound engineers, they're actually making very, very, very good. Actually, it's actually more in domain of creative industry and art than some solid engineering and science. So one notable example of an attempt to actually make some systematic framework is ambisonics, which is actually aiming, unfortunately, at the physical approximation in the center of the listening area. And because of its sort of conceptual complexity and the lack of stability of this sweet spot, has never become widely represented in commercial systems. So towards achieving convincing spatial sound, we are now talking again about these 5 to 10 channel systems where we actually need to rely to a large degree on psychoacoustics. There are several technical challenges that need to be overcome. One thing would be sort of to answer what would the minimal number of channels that we need to actually have 360 degrees perspective. And we cannot really be too ambitious with a small number of channels. So what we want to say, well, let's be happy with just having a satisfactory 360 degree auditory perspective and have the satisfactory spaciousness experience, and we are going to limit ourselves to that. So, and there was some earlier work in the domain of psychoacoustics on Fletcher and Ando and Kurihara. Fletcher actually figured out that 3 channels is minimum for providing perspective to the front of the listener in horizontal plane. Then we are thinking, well, 2 more channels should be sufficient, or would be the minimum to extend that perspective to 360 degrees. And there was also work by Ando and Kurihara from the 80s, which established that minimum 5 channels is also minimum to create a proper diffuse sound field, so the listeners cannot really sort of say that a sound source that cannot identify isolated discrete speakers in the space. So we're starting with 5 channels, and now another question is what would be the optimal playback scheme, and to that, in order to answer that question, we are sort of looking into also early work by Fletcher, which established that actually any kind of mixing between channels somehow blurs the auditory perspective. So what we are doing is, well, we're going to start with the minimum of 5 channels, and each microphone is going to have dedicated loudspeakers, so we are not going to do any kind of mixing, and whatever we record, that is what we are going to play back. Now, the most difficult question, and something that people didn't really research much, was, well, how to optimally acquire the sound field, or what is that we need to capture about the sound field to reproduce it, which amounts to sort of designing proper microphone array. And that is actually what most of our research is about. And how we do that, that is explained in one of these posters. But basically, what we are going to present here is a systematic design framework for multi-channel surround systems, which is going to work for an arbitrary number of channels, I mean reasonable number of channels, starting with 5 and on, and which is going to be applicable to any kind of circular distribution of loudspeakers. Can be 5-1, can be regular configuration, etc. Then it turns out that actually, in order to capture desired sound field cues, we would actually need to work with higher order microphones than what is currently really available. So then we were sort of wondering whether that is possible to produce. And to that end, we actually developed a new class of high order differential microphones, which are actually practical and feasible, and we even built a very, very cheap prototype. So recording technology is quite possible. So when we started this research, we were actually motivated mainly like, oh, we want to go to Carnegie Hall and record the performance and then play it back. So classical music aficionados would be happy, but actually there is much larger market for virtual reality, audio games, etc., where we're actually synthesizing sound field. So starting from a physical microphone array, which is capable of recording sound field in a way that we can reproduce it and feel transposed to that space, what we can do is that we can just sort of measure impulse responses with respect, or calculate that microphone array, and then if we happen to have some virtual reality application, we can just convolve sound sources with those impulse responses, and that is what we are going to play back. However, if you want to render dynamical soundscapes, then that becomes computationally very, very expensive, because particularly in video games, actually most of computational complexity is allocated for delivering video content. Therefore, we would need something which is going to work really, really well and do not really require much of computational complexity. Therefore, we developed a scattering delay network, which is nothing else but software implementation or reverberator, which is based on our technology, but is actually compatible for any kind of different surround sound technology, which is going to provide super real-time rendition of dynamical soundscapes. And we have here one demo. You're going to see that's going to work really well. Even there is iPhone application or little demo which you can try, and you're going to see how basically little sound source is going to move as you move your head, and there is accelerometer there which is going to track movements of your head, and actually I was quite impressed. Answer just created this, and I had no clue that it worked that well. So, and also another side result was a computational model of perceived source direction and locatedness. So where we are actually we want to be able to somehow evaluate how certain system is going to work without actually going into very extensive and tedious listening tests and so on. And that is something that we developed for this purpose, which of course works for any kind of other surround sound system. And actually we were quite happy with the level of agreement of listening tests with our model. So, but all the details of all that is on these posters, which you're welcome to visit. I think I'm a little over time. Maybe 5 minutes. Okay.
Well, maybe we should proceed then
Sure.
directly to Tiana. Yeah, thank you, Zoran.
Sure. You're welcome.
Should be right back.
It should be fine. Oh, yes. Sorry. Yes, just. Okay, thanks.
Thank you.
Good evening, everyone. My name is Diana Salazar. I'm a lecturer in music here at City University, and welcome to our performance space, which is right at the heart of the music department here at City. I'm one of 3 teaching research members of staff here teaching in composition, but also dealing very much with music technology, and that's something that's at the heart of the music department here, is this engagement with music technology and composition, and looking at how we can map intersections between those two areas. There is a growing community of composers engaging with music technology at all levels in the department, so I'll be taking a look at that this evening. I'll give a short overview to where music technology is embedded in the Department of Music here at City. I'll take a look at our facilities, but you will have an opportunity to look at our studios and actually look at some of the work that's being created in the studios here after this presentation. I'm going to take a very quick look at some of the research that's going on, staff research and student research, PhD research in music technology and composition. We'll look at some recent successes in the departments that we're very proud of, and where the department might be going over the next year or so. So I mentioned that composition and music technology is important not just at a research level, but it starts right at year 1 of our undergraduate programme in music. We have a broad-based BMUS here, an undergraduate programme, and right in the first year we start introducing students to music technology, but in the context of a composition module. So what's very important to us is that students are engaging with software like Logic, but thinking about how they're applying those skills in order to create interesting, innovative, new creative work. In the second year, we form 3 strands where students can study studio composition, composing for moving images, and also instrumental and vocal composition. And then there's also an option to do studio recording here, and you'll see our studio later on this evening, where students work with classical-based recording, but also they look at multi-track popular music recording. In the third year, we strongly encourage students to think outside the box. So we've had students working in their third year developing new instruments, using sensors and mapping the data onto sound in order to create sort of interesting new performance-based projects using music technology. And we have students working in studio compositions, surround-based work, and composing for moving images as well. To tie in with that, we have a new experimental music ensemble comprising both undergraduate and postgraduate students, creating, realising existing works, but also working with music technology and improvisation. At postgraduate top level, we have 2 degrees. We have a new composition degree this year, which is a composition degree that considers composition as something that's very broad, that encompasses both notated composition, but also digital musics as well. So we have students working again in the studios, developing surround-based work, working in an interdisciplinary context, developing sound art, work with live electronics and live performance and so on, as well as what you might traditionally think of as composition with scored music. We have an MA in Composing for Moving Images that runs alongside that, where our students work on a range of projects utilising the studios to create soundtracks for live action film, animation, and also looking at collaboration. So we've had some really interesting work with dance over the last year. And then, of course, we have students working on industry placements as part of that. So we've had some students engaging with media production companies locally. At PhD and staff research level, this all sort of follows in a long strand. So we have a member of staff working primarily in moving image work and also doing research aligned to that, more theoretical research. I myself work in sound in studio composition and sound spatialization. We have a member of staff working in instrumental music with live electronics and looking at the relationships there as well. But I'll go into that in more depth in a few slides' time. We have a range of events, including this, as part of our concert series, which takes place on Tuesday evenings, where we have visiting composers, performers, and speakers from the UK and beyond speaking here. And that really informs not only our PhD and staff research and also enhances our network, but also feeds into our top programmes. And things like our research seminar series and City Listening Group, which is a group where we listen to and discuss music, feeds into our research as well. We're very lucky to have some ensembles in residence as well, so Plus Minus Ensemble is integral in allowing us to explore instrumental music composition, and they're open to work with live electronics as well, which works extremely well within this framework. So just to give you an overview of our studios, which you'll see later on, we have 6 composition studios. 3 of them are surround, so we have 2 5.1 studios and an 8-channel studio, as well as 3 smaller stereo studios. And those are used for a variety of different kinds of work. You've already seen that moving image work is very important to us here, and so some of the studios are used sort of as post-production studios in that line of things. We have the recording studio, and this room itself can actually act as a large live room, a flexible live room for the recording studio. It's set up to an industry standard. It's a very flexible space. We have the audience desk, and it's a space that's in demand not just by our students, but also by sort of commercial companies. We had the BBC in this weekend recording a new documentary called The Sound of Soul, and they were recording both in here and also in the studio itself. We have an isolated live room and a vocal booth as well, either side of the recording studio. So it is a very flexible space for staff and students. We also have digital controllers, outboard effects, the usual sorts of things, and we're very well equipped with sort of standard industry software. In the equipment store, we have plenty of commercial microphones available to students, but we also have things like the Soundfield microphone for multi-channel work. And that's all supported by a specialist studio manager and a technician. So let's take a closer look at some of the research going on here in music. Dr. Miguel Mera is a specialist in film music composition, both practice-based but also the theory behind that. He is active as a composer, but most recently he's been working on a new work, Morena, for dance, and that was premiered just before the summer at the Laban Theatre, Trinity Laban Dance College. He's also been engaging in some projects alongside informatics, one of which is looking at audio-visual attention. So analysing in quite an empirical way how music might affect visual attention in particular audiovisual scenes. In addition, he's also very interested in live music broadcasting. So for instance, things like the broadcasting of the proms performances and how the edits are chosen in relation to points within the music. Dr. Newton Armstrong is a composer of instrumental music and works for both studio composition but also instruments and live electronics. And he's very interested in this relationship between performers on stage, instrumental performers, and the live electronics, real-time processing of sound, and how musical structures are formed using these components. He's designed a lot of home-built instruments for performance, including improvised performance, and he's very experienced in using sort of hardware to design his sort of custom-built instruments for performance. He also has an interest in analysing how we listen to these types of music that might involve both performed instrumental sounds and electronic sounds. And he's very interested in how we adjust our listening into different modes within these situations. Myself, I am primarily a studio composer. I work very much with recorded, sampled materials and processing of materials and spatialization of those materials. But in recent years, I've become very interested in collaborative performance, and one of my recent works has been alongside a dancer, looking at real-time tracking of her limb movements using very small accelerometers and mapping that information onto sound sets. Then analysing the relationship between the dancer, movement, and the sound space. So that's one of my current projects. But I also have an interest in music technology pedagogy, particularly laptop orchestras, and how new modes of learning can be developed within a collaborative performance environment using music technology. I'm going to hopefully try and play a short example of my music, but there are plenty of examples installed in all of our students here for you to peruse at your leisure after this presentation. So this is a short example from a recent fixed media work of mine, a recent electronic work, using just samples of chopped chilies. That's the only source material. Small section. So we have a very strong PhD and MA community here who are very active, both within the university but also at sort of national and international levels. So these are some of our recent successes. PhD student Georgia Rogers, who I believe is in the room tonight somewhere. Yes, was selected for the Sound and Music Higher Education programme, where selected student composers were essentially commissioned to produce new works. And I believe Georgia has just finished, is that right? Just finished a new work for tuba and live electronics, which will be premiered at Huddersfield Contemporary Music Festival and also released in CD. We've also had a student recently shortlisted for the Oxford Sennheiser Electronic Music Prize. A I've just mentioned Miguel's work, Morinha, was premiered just before the summer. I was awarded something at some point, and Newton Armstrong's works are performed regularly both in the UK and internationally. And we keep our blog updated with our student successes. Future plans, well, we have sort of growing links with external industry and research organisations. I just mentioned the BBC were in filming a new documentary over the weekend, and we've had some students have work experience with local media production companies. Just even last night, Dr. Miguel Mera was chairing a conversation with Patrick Doyle, quite a well-known composer for film, at the Royal Albert Hall, part of a BAFTA series in conversations with composers. We have a project developing with the Museum of London and our studio composers, and we have links with Exaudi, a fantastic vocal group that's London-based, and of course Plus Minus Ensemble, who I've just mentioned. And of course we have sort of ongoing improvements to our studio facilities, and we are looking at our undergraduate programme and thinking about possibly developing a programme to exploit our particular strengths in this particular area. So I think I'll move on to this next slide. But Tilman, do you want to sort of go over what the plan is next? Yeah, well, that's me finished, and we have a variety of different demonstrations in the papers here. So please do ask questions, and I'll unlock the studios so that everyone can have a listen to some of the work that's going on here in composition at City.
Thank you very much. I personally have a lot of questions for the track that you played, and also to the two presenters. Maybe we can go together and have a look at the studios, and then we can ask all our questions directly to our presenters. And thank you very much.